I'm going to start today by reading an excerpt from a description of an earthquake and tsunami that hit the Banda Islands in East Indonesia back in 1852. With the first earthquake shock, which quickly turned into an undulating motion, the majority of Banda's dwellings or outbuildings were in ruins, or they were damaged so badly that they became uninhabitable. Less than a quarter of an hour after the earth was at rest again, a seaquake arose, which surpasses all imagination. Many people were killed by this disaster. The damage suffered on the Banda Islands is so great and so universal that the monetary value of it cannot be calculated, and it will never fully recover from this event. Now, this is a really sad story, but it's even sadder when you go to the Banda Islands today and talk to the descendants of the people who survived this event, and they don't even know that this ever happened. They don't understand the risk that they are in living in the same place that their ancestors lived and potentially suffering through the same things that their ancestors suffered through. So in Indonesia, there's a real problem with understanding risk and a problem with communicating it, which is something that I'm hoping to improve with my thesis. With all that being said, my thesis is on field investigations and numerical modeling of earthquake, tsunami, and landslide risk in eastern Indonesia. We're going to go through 5 chapters today. The first is a general introduction. The second is on quantifying earthquake risk through geophysical surveying. The third is on modeling a volcano sector collapse landslide. The fourth is on tsunami sedimentology, and the fifth is on using Bayesian statistics to identify the source parameters of a pre-instrumental earthquake. I'm first going to start with a quick intro to the region's geology as well as its hazards. Indonesia is a country that's mainly made up of subduction and collision-related island arcs. The Australian plate converges north, and the Pacific plate converges west onto the Eurasian plate, which results in this subduction zone called the Sunda-Banda arc. The Sunda arc is produced by the subduction of oceanic crust at an oblique to 90-degree angle from the trench. My research involved 2 areas along the Sunda arc. The first is the city of Pacitan on the island of Java, and the second is the island of Lombok. The boundary between the Sunda and Banda arcs here is defined as the point where Australian continental crust starts going into the subduction zone. The Banda arc is directly impacted by this and the westward motion of the Pacific plate, which results in a subduction zone that rotates 180 degrees as you move east. Another 2 of my research areas, Ambon and the Banda Islands, are located within this hook here. Because of Indonesia's active tectonics, geologic hazards are a regular threat here. The human impacts of these hazards continue to increase in severity as the population increases, though. Understanding these hazards is crucial for mitigating their effects and for preventing future disasters. Broadly speaking, my thesis focuses on earthquake, landslide, and tsunami hazards in these areas of Indonesia. The first study in my thesis is on time average shear wave velocity to 30 meters depth, or VS30, in different parts of Indonesia. The most obvious attributes that can control the level of shaking a particular area experiences in an earthquake are the epicenter of the earthquake itself and the distance, or the magnitude of the earthquake itself and the distance that you are from the epicenter. However, the past century of studying earthquakes has taught us that the geophysical characteristics of the site itself can also have a big impact on the shaking intensity. Earthquake waves can travel a lot more quickly through solid, well-consolidated rock than they can travel through poorly consolidated sediment. When these earthquake waves are forced to slow down, though, they respond by increasing in amplitude. This example here shows how a wave might change as it travels through different types of subsurface. It's going to pass through solid bedrock the quickest and with relatively low amplitude. And then this water-saturated sand and mud is going to have the waves traveling the slowest and then also with the highest amplitudes. This means that with everything else equal, you can expect to get your heaviest shaking over in here. This concept can be quantified using a number that's called VS30. This is the average shear wave velocity of the upper 30 meters of the ground, which means that with a lower VS30, you could expect to have more heavy shaking. The International Building Code uses VS30 as a proxy to understand seismic risk at particular sites. By using VS30, they assign any given site a site class ranging from A to E, and as these letters increase, so does the risk. With this system, you can easily communicate the standards that buildings in a particular area need to be built to in order to withstand an earthquake. For this project, I calculated VS30 for 58 different sites in the city of Pacitan and on the islands of Lombok, Ambon, and the Banda Islands. We did this through a technique called MASW. This technique's pretty well established, so I'm going to skip over the methodology details for the sake of time, but the gist of it is that we produced our own earthquakes using a sledgehammer and then measured those Rayleigh waves using this line of geophones here. I then compared those VS30 values to the distribution of local geologic units, as well as MMI observations for recent earthquakes, which I'll talk about more in just a little bit. The major question to answer here is whether VS30 values correlate with MMI and local geology in these areas, and whether the VS30 values can be used to predict shaking intensity at a given location during an earthquake. For the sake of time, I'm kind of going to skip over the method section like I mentioned before, but here are my results. The Pachitan region here varied from around 150 to around 750 meters per second. All of the lower values are located on the alluvium here, these blue dots, and the lowest values are in the center of the basin and closer to the ocean. The one very high value is up here in the mountains, located on the Arjosari Formation. This formation is composed of a lot of different sedimentary and igneous rock types that aren't differentiated on geologic maps, so I can't give you an exact rock type for this site specifically, but it's likely a much shorter distance to bedrock here than it is in the basin. The percent fit between the measured dispersion curves and the modeled dispersion curves, which can kind of be used as a number to help you understand the expected accuracy of your VS30 measurement, has a mean for these sites of 95%. There was only one measurement that had a percent fit of less than 90%. And then for this interpolation you can see in the background, this was done by considering both the VS30 measurements as well as the surrounding geology. And then on that I added lines corresponding to NEHRP seismic site classes. For areas with a denser concentration of measurements that have the same geologic ground type, I just interpolated between those directly. However, if you use this technique on measurements that are spaced farther apart and have different geology, like this and this one up here though, you're going to get just a normal interpolation will give you a pretty diffuse transition between the two. That probably isn't accurate when you consider that geology appears to have a significant effect on the VS30 values. So in these situations, I incorporated known geologic unit boundaries to act as site class boundaries. So for Pachitan, the basin is site class C to D, while the hills are more likely class B based on this one measurement here. Until we get more measurements though, this rainbow interpolation in the background should be considered estimates rather than definitive numbers like these individual measurements are. What's interesting about Pachitan is that the velocity typically decreases as you move towards the center of the valley, which is most likely because sediment thickness increases away from the hills and closer to the coast. And you also have an increase in water saturation closer to the ocean here. These are my results for Lombok. You can broadly divide the sites into two different ground types, alluvium and volcanics. The volcanic sites are actually three separate units, but most of them are in the Leko Pico Formation. The measurements on the Kalibabak Formation and the undifferentiated volcanic rock of Rinjani are within the range of values for the Leko Pico Formation, so with this dataset there's not enough evidence to give them their own velocity ranges. The mean VS30 for the alluvial measurements is a lot lower than it is for the volcanics, although there are some lower outliers for the volcanics right here in northwest Lombok. The mean percent fit of the model dispersion curves is a little bit lower at 94%, and this was the area where I had the largest number of measurements that had a percent fit of less than 90. I had 4 of them out of the 20 have a percent fit less than 90. Again, for the interpolation, I used the same technique of combining direct VS30 interpretation with interpolation with geologic interpretation. The alluvium in northeast Lombok has a site class that's as hazardous as D, but most of it is C. You've also got this tail of C-class measurements that stretch out into the coastal volcanics up here. Only one measurement was taken outside of North Lombok, and I'll mention why in a bit, but this measurement is the one that's here in Mataram. It came out as C-class, which concurs with the other alluvial measurements we have, and from these I inferred that the other alluvial deposits on Lombok are also most likely class C, and your volcanics are likely class C to B. You'll notice here that I excluded a good part of South Lombok from any interpretation. The reason for this is because it's underlain by sedimentary bedrock here, like limestones and sandstones, and I don't have any of that on Lombok that I took VS30 measurements on to be able to draw estimates from. So for the sake of not making assumptions where I don't have enough evidence, I just left that out of my interpretation. In addition to calculating VS30, I made maps of MMI for 3 different events that have happened in Lombok and Ambon. MMI stands for Modified Mercalli Intensity, and this is a qualitative way of describing the damage that was experienced in an earthquake, whereas VS30 is more quantitative. For MMI, the shaking intensity can range from 1, which is not enough to be felt, to 10 or 11, which is total destruction. MMI is really a simple way to compare VS30 to the shaking intensity of real-world earthquakes, and it's especially nice to have because you usually don't have a lot of seismometers scattered around that might give you, good quantitative measurements, so you kind of have to rely on this qualitative information. Northern Lombok had a series of large earthquakes back in 2018, which caused some pretty significant damage, and this was mainly why I wanted to focus my VS30 study on this part of the island. The first earthquake was the smallest of these, but this was actually the earthquake where the Indonesian government went out and collected MMI observations for this event specifically. So I mapped the locations of those observations and interpolated between them to make this map here. The epicenter for this event is located right where this black star is, and the most damage was occurred in this area here. Although notice that a bunch of locations on this whole map can have several points of variation within a pretty short distance, like this one where you have 6 to 8, or over here on the other side where you've got range of 5 to 6. If you think about this map with respect to the VS30 map, there's quite a bit of dissimilarity between the VS30 measurements and the MMI observations. So if VS30 alone was the only determining factor for MMI, you would expect to see higher values here, and lower values here, whereas you kind of see the opposite. This could be due to a combination of different factors. The first and most obvious one is the distance from the epicenter. If a site is close enough and your conditions for the earthquake are right, the impact of being located right by the epicenter can override the fact that you're on high VS30 land, and you could still get significant shaking. Another factor could be geologic units that aren't mapped in sufficient detail. The only geologic map of Lombok I had to work with was 1 to 250,000 scale, meaning that the boundaries and units that you map with are forced to be, somewhat simplified. It's possible that pockets of different units might exist in these areas that aren't mapped on the one geologic map we have. Another characteristic you have to remember is that these earthquake waves aren't traveling through homogeneous rock. Heterogeneity caused by different types of rock that each have their own geophysical properties can cause irregularities in how that energy propagates, and this would require a more complex model to understand than what I did in my thesis. Finally, the only geophysical characteristic this study addresses is VS30. It's totally possible that other variables like the dominant frequency and shear wave velocity gradient could also influence site response. Here are my VS30 results for Ambon. The geology of the sites here is a little bit more variable than it was for Lombok or Pacitan. There's still measurements on alluvium, which are yellow here, or volcanics, which are red, but then you've also got several measurements that were taken on limestone, and one that was taken on ultramafic rock. The mean VS30 for the alluvium was slightly higher than in Lombok or Pacitan, but it was still site class C. The volcanic and ultramafic sites had a mean of 501 meters per second and were site class B, while the limestone was kind of intermediate between the two and was site class C. The lowest VS30 on Ambon was recorded right here, right kind of towards the edge of the bay, in an area that we refer to as Rumah Tiga. The percent fit of all these dispersion curves was 94%, and there were two measurements that were less than 90% fit. Now, something that happened that was sad but maybe a little bit of a happy coincidence for this thesis was that just a couple months after we took those measurements, there was a magnitude 6.5 earthquake that struck Ambon. And because this happened after we took our measurements, we actually asked the government when they were out taking their damage surveys to visit the same sites that we took our MASW measurements on. And this allows us to directly compare the MMI and the VS30 at the exact same locations. So they found that for the built environment, MMI generally ranges from 4 to 5. However, right here, MMI was 7. This makes sense because this was where our lowest VS30 was anywhere on Ambon. Some of these, though, make a little bit less sense. Like, for example, right here, this is on alluvium, but we have an MMI of 4. This is also an alluvial delta. This is an MMI of 5. So some of these, this one totally agrees with the VS30. Some of these other ones don't. And again, this could be due to the same factors that I discussed on the Lombok image. It can be because of heterogeneity in the way that the earthquake waves are propagating. It can be due to differences in site response or other factors. The second earthquake I'm going to talk about for Ambon actually happened in 1898. We don't know what the magnitude was or where the epicenter was, but we know it caused severe damage in Ambon based on the records of it. I looked at written descriptions and photographs of the damage in order to estimate MMI in different parts of the island. I then mapped and interpolated those observations using old maps to help give me an idea of where particular spots are located in modern Ambon to produce this map here. You can see that the average MMI is greater for this event than it was for the 2019 event, and here the most severe damage was in the city of Ambon itself, where it's potentially as high as 10, but then again in the Rumah Tiga area. So Again, this kind of makes sense where you have your highest MMI values in areas with low VS30 because they're located on that soft alluvium. But again, you still have some spots where the VS30 is, or the MMI is a little bit lower than you might expect. So again, there are other potential factors that can be at play here. Finally, these are my VS30 results for the Banda Islands. Like Ambon, there are sites located on alluvium, limestone, and volcanics here. The sites on alluvium have a relatively low mean VS30 of 231 meters per second and range from site class C to D. The limestone and volcanic sites were both significantly higher than this and were class B, although I only have 2 measurements of the volcanics and 1 of the limestone, so this is kind of an estimate for these areas. It would be really great to be able to get more VS30 values for the volcanics and the limestone, but once you get out of the alluvium, it tends to get extremely forested, and it's hard to find an area that's long enough for your line of geophones. So the overall purpose of this study was to calculate VS30 for regions of Indonesia where it had previously never been measured, and to use these data in conjunction with known geology and MMI observations to identify areas where the risk of structural damage is the highest. Overall, this research corroborates VS30 studies that were done in other areas, which have found the lowest VS30 values are generally on deep, unconsolidated alluvium. This also tends to be where the greatest number of people live in these regions, which is unfortunate. These findings highlight the importance of improving the resilience of Indonesia's structures against earthquakes in these areas. These measurements also act as foundational work for understanding how VS30 can vary in the areas that I surveyed. In the future, increasing the density of measurements as well as measuring other site characteristics could help to improve the accuracy of these risk maps. I also hope these findings can be used to educate the communities involved in order to improve their infrastructure and mitigate future earthquake hazards. Chapter 3 of my thesis is on the potential sector collapse of Banda Api, which is a volcano located in the Banda Islands. This study focuses on sector collapse tsunamis, which you might refer to as the silent killer tsunamis. Back in 2018, a tsunami struck western Java and southern Sumatra at about 9 p.m. There was no earthquake or receding of the sea or any other warning. This is a video of a concert that was taken on the beach just before this tsunami event. So again, these happen really without any potential warning for the people who are at risk. So the tsunami we just saw was produced by this sector collapse here. This volcano is named Anak Krakatau, and it's built on the rim of a larger caldera that collapsed about 1,500 years ago. This photo shows how much material was involved in the 2018 slide. This sector collapse made a tsunami that devastated the nearby coastlines without any warning, killing more than 400 people and injuring 14,000. Anak Krakatau has both geomorphological and geochemical similarities to Banda Api, which is a volcano located on the other side of Indonesia. The purpose of this project was to determine the effect that a major sector collapse of Banda Api would have on the other coastlines in the Banda Islands. Because there's no active monitoring of Banda Api taking place right now, and because a large percentage of the Banda Islands residents live near the coast, understanding whether this is a significant hazard is really necessary for determining whether more active monitoring of its slope needs to be happening. Banda Api is right here. This is the only active volcano in the Banda Islands. It's one of the 3 central Banda Islands, the other 2 of which are older collapsed calderas. And while the island itself is about 600 meters tall, if you include the mass of the volcano below sea level, that adds another good 5,800 meters to its height, making it unusually large for a volcano in this geologic setting. Banda Api has got a long history of eruptions. The most recent of these happened in 1988, where volcanic activity was concentrated on fissures on the north and south slopes of the volcano. The arcuate line that's delineated by these features, which I've highlighted here, you'd expect this to be associated with an increase in fracturing and a general weakening of the rock. The concern with that is that this might be showing a zone of weakness along which a future sector collapse could occur. Along with the fissure eruptions, there's a couple other indicators of potential slumping or a sector collapse. One is the fact that the west side of the volcano's crater is significantly lower in elevation than the east side. The other is the presence of a north-south striking normal fault I mapped right at the summit. To model the collapse, I used a program called Tsunami Squares. The most important inputs for this program are the geometry of the sector collapse and the topography and bathymetry of the surrounding area. To model the geometry of the sector collapse itself, I started onshore by mapping this exposed fault. This fault's located at the summit and dips steeply to vertically, indicating that it probably propagates deeply into the volcano. Again, it's only visible at the summit where there's not a lot of vegetation, but if you extrapolate it north and south into the trees, it essentially connects with the 1988 lava flows. The line formed by the fault and the lava flows produces this curved plane in cross-sectional view. If you take that curve and extrapolate it out to where the dip becomes horizontal, you can estimate the offshore and onshore extent of the landslide. The other important part of this model is the topography and bathymetry that's involved. The onshore topography was pretty straightforward. I just used a DEM produced by NASA. The offshore bathymetry, though, was a lot harder. The only bathymetric DEMs available were so low resolution that any tsunami model wouldn't be accurate, because nearshore information or nearshore resolution of your bathymetry is really important to be able to accurately model tsunami wave propagation. So I made my own bathymetric map that I merged with the topography. I used both modern contour data from the Indonesian government, as well as sounding measurements that were taken offshore around the Banda Islands back in the 1920s. To make sure that those sounding measurements were accurate, I took sonar equipment to the Banda Islands and cross-checked them in several different locations to make sure that the values lined up, and they did. So once I took all of that, I interpolated it together into a single topo bathymetric map, and I fed all of that into the program, along with giving some reasonable defaults for other coefficients that determine parameters like friction and acceleration. And this is the resulting model, both in map view up here and cross-sectional view at the bottom. This sector collapse landslide produces an enormous tsunami that starts by propagating out towards I, but the waves reach essentially every part of the coastline within about 6 minutes. An important part of these results, though, is that this first wave, which is formed by the water displacing the landslide, I'll show right here, it essentially bypasses Lonthor Strait and Uzgat Strait and doesn't make it into the bay. However, the water that is displaced by this rushes back in to fill this and shoots up the slope, you can see right there, and that second wave is able to make it into the bay. You can see right here, it does get into the bay. This is a concern for me because a pretty large part of the Banda Islands population lives on the coastline along this bay in here. Here's a map of the wave heights at specific points on each island. I sees the highest wave heights at more than 80 meters tall, and almost the entire island gets inundated. Rune also sees really high wave heights at 66 meters, although there aren't any people living on the side of the island where the waves are the highest. However, where people do live, the wave heights are still more than 20 meters. Hatta, which is on the other side of the archipelago, is hit last and also gets the lowest wave heights. The wave height here is only 5 or 6 meters on section of the coastline where people are living. But 5 to 6 meters of water is still a lot of water. The results for the central Banda Islands, like I mentioned before, are more interesting, particularly within the bay. So even though that first wave can't get into the bay, the second wave does, and it makes these really high wave heights on Banda Api. But that produces wave heights of a good 15 to 30 meters or more in places where people are living along the bay. To better understand the implications of these results, I mapped the location of each building on the islands as well as the overall inundation. From this, I found the number and proportion of buildings that were inundated on each island. The most recent census of the Banda Islands gives an overall population for the archipelago, although it doesn't give you population for each island. In order to estimate that, I divided the population evenly among the number of buildings to get both an idea of the total population on each island and the affected population on each island. Overall, this comes out to about 13,000 people living in the sector collapse inundation zone, which is 63% of the total population. I is the worst affected percentage-wise, with 100% of the people getting inundated. However, Nira is the worst affected in terms of raw numbers. Even though it only has 68% of its population inundated, that's still close to 6,000 people, since Nira is the most populated island to begin with. These numbers are really concerning because when you consider how quickly this whole event can happen, waiting until the full collapse starts to start evacuating people isn't a viable approach. I go into more detail on this in my thesis, but the best way to mitigate this hazard would be to install an array of GPS receivers on Banda Api. This would tell you whether any slow creep is already happening, and if that creep starts to accelerate, it would give you potentially enough advance warning to evacuate everyone to a safer location. So just to summarize, the purpose of this study was to determine the most likely way a sector collapse of Banda Api could happen, whether this would produce a tsunami of significant size, and what effect that would have on the people in the Banda Islands. I found that, along with evidence of creeping of Banda Api's west slope, a tsunami produced by this collapse would inundate a majority of human structures on the Banda Islands. These findings showed the importance of setting up a GPS array on Banda Api to better quantify any future creep and to give advance notice of a pending sector collapse. It would also be helpful for additional field surveys to be conducted on Banda Api in the future, particularly on those north and south slopes, to try and map that exposure of the feldspar past the summit. Along with all this information, I think that it's important that this communicates that people need to start planning for the event of an emergency evacuation of the Banda Islands, because this is something that you really can't afford to wait until it's time to evacuate before you start putting together a plan. Chapter 4 of my thesis is on tsunami sedimentology, primarily in the Banda Islands, but a little bit in Ambon as well. Major earthquakes and tsunamis are a frequent problem in the Banda Islands. This annotated photo here shows the estimated run-ups of 4 different events on the island of Nira, and this is only in the past 400 years. However, they haven't had a major tsunami since 1852, so often people living on the island don't have any idea that they're living in a tsunami inundation zone. This is a table of the major earthquakes and tsunamis that have been recorded in the Banda Islands. The frequency of these events makes sense when you consider that the Banda Islands are surrounded on 3 sides by subduction zones. But the main purpose of this study was to determine whether there's any sedimentological evidence of either historic or paleo tsunamis in the Banda Islands, and whether any of these deposits can be temporally constrained using dating techniques. I dug 6 trenches in the Banda Islands to search for evidence of tsunami deposition. Some examples of tsunami deposit traits I looked for include the presence of marine carbonate sand grains, the presence of larger coral or shell clasts, bimodal grain size distribution of the sediment, or tsunami structures like rip-up clasts and scouring. Since the area has been pretty densely populated for hundreds of years, I also wanted to explore whether broken human artifacts could be associated with tsunami deposits, because it does seem reasonable that an earthquake could cause a bunch of destruction of human items that could then be buried by tsunami deposition. Along with the Banda Islands, I also dug 1 trench on the island of Ambon to look for tsunami deposits there, but also to better understand how the depositional processes of the Banda Islands might vary from those of other islands in the Banda Sea. The techniques I used for constraining the ages of my candidate tsunami deposits include the carbon dating of carbonate and bone, optically stimulated luminescence dating of sediment, and typology dating of artifacts. From the trenches, I identified 10 different sediment facies. These each have their own characteristics, but they can broadly be lumped into a few different depositional environments. The first facies is interpreted as a cultivated or otherwise organic rich soil. It's found in 4 trenches in the Banda Islands, but only at the top of each trench. Facies 2 through 4 are interpreted to be marine sediment. The main thing these facies have in common is the presence of sand-sized shell and coral fragments within the sediment itself. Facies 5 through 7 are interpreted as onshore tephra. These are grains composed entirely of volcanic rock and glass with no carbonate sand grains. And then the last 3 facies are only found in the trench on Ambon. I wanted to categorize these separately because Ambon has some significant differences in both the types of sediment and the sediment transport processes that are available there, such as fluvial systems. Facies 8 has large limestone clasts, which could be marine or colluvial, but I suspect are just anthropogenic because it was pretty close to the surface. Facies 9 is most likely marine, and Facies 10 is most likely fluvial. Now I'm going to talk about the individual strat columns in a second, but what I observed overall was that there was kind of a significant amount of variation between the trenches, both in which facies are in which trench and in what order those facies occur. Because of this, I couldn't really correlate units across the trenches. It was also surprisingly difficult to identify tsunami deposits in the trenches, despite the fact that we know tsunamis have happened here, and for some of these trench locations we know specifically that that spot was inundated. Only 3 of the trenches contained marine source sediment at all, and 2 of those trenches had no other non-marine sediment. Coral and shell fragments that are cobbled to gravel to cobble sized were present in a lot more units though, so if you take those into consideration, it widens your scope of potential tsunami deposits pretty significantly. However, these units didn't consistently have other traits that could indicate tsunami deposits, like the bimodal grain size distribution of sands or erosional bases. One thing to note though is that the idea of bimodal grain size distribution kind of depends on how you're defining your grain sizes, because if you want to include those intermittent gravel to cobble-sized carbonates, you could argue that most of the units in the trenches are bimodal. Horizons that had larger marine fragments also often contained anthropogenic artifacts like porcelain, glass, or pipe fragments, but again, the issue of missing tsunami traits also applies to these units. So, overall, while this study has identified a number of candidate tsunami deposits, these should only be considered potential tsunami deposits rather than definitive ones. I used several different techniques to constrain the ages of the candidate tsunami deposits, and these had varying degrees of efficacy. the radiocarbon dating of carbonates produced ages that are most likely overestimates. For instance, a given shell might produce an age of maybe 1,000 years ago, when you can still find colonial artifacts for another meter beneath that that you know are 400 years old or younger. The most likely reason for this is that a shell in coral can persist off the coast of the Banda Islands after the animal dies for hundreds or maybe thousands of years without fully breaking down. So even though the age of your carbonate might be technically correct, it's not necessarily an indicator of the age of the sediment deposition on shore. I also carbon dated several animal bone and tooth samples when I observed them. These produced ages that were consistent with artifacts found above and below them, which makes sense because a bone is much more likely to break down faster than a carbonate if it's not buried fairly quickly. Otherwise, it'll just decay in the hot, wet, humid Banda Islands climate. Along with that, I took 4 OSL samples. Like with the carbonates, these ages appear to be overestimates in every case where they could be compared to the depth of datable artifacts. This is most likely because the samples were found to be partially bleached, which means that the luminescence signal didn't get completely reset before they were brought on shore and buried, or after they were brought on shore and before they were buried. It turns out, though, that one of the most useful ways to constrain the ages of deposits in the Banda Islands is through the typology of artifacts. Particular kinds of porcelain, stoneware, and pipes are associated with particular time periods of production. This doesn't tell you the minimum age of the deposit because the artifact could have been kicking around for a long time before it was buried, but it does give you a maximum age. With all that dating information, I took the best candidate tsunami deposits and identified what events they're most likely associated with. In BA1, I have 3 candidates. The lowest of these contains grain-sized or sediment-sized carbonate fragments, and by carbon dating a bone that was found in this unit, I identified that this is most likely associated in time with the 1778 event. Then we have 2 other events. This one here contains hard pan, shell, and coral fragments, as well as some anthropogenic items like porcelain and kaolin pipes. And this one is most likely associated with the 1854-41 event. This event up here contains calcareous sediment, as well as coral and shell fragments, and some brick pieces, and some carbonates, and some hard pan. And if this is the 1841 event, this one would most likely be the 1852 event. In Trench BA2, I identified 2 candidate tsunami deposits, but first I found a piece of stoneware right here that was associated with a production age of 0 to 1000 CE. That would mean that this stuff down here, if it's a tsunami deposit, would be an indicator of a prehistoric tsunami deposit. This contains coral pieces, a lot of volcanic rocks, as well as a pretty large cobble of a Tridocna shell. And then up here I've got this deposit that has coral fragments in it. Again, we know that it's younger than 0 to 1000 CE, but I don't have any other datable information aside from that. So this could be prehistoric or it could be historic. In Trench BA3, I identified 2 candidate deposits. This one right here is most likely associated with the 1778 event, and that is based on artifacts as well as carbon dating of tooth fragments. This contains, along with the artifacts, this contains some pieces of coral and volcanic rock. If this is the 1778 event, then this one down here is most likely the 1629 event. This one contains coral, hard pan, as well as brick, volcanic rocks, and stoneware. This trench, BA5, is one of those trenches that had marine stuff the entire way down. So I have a unit here that I've identified as a candidate tsunami deposit based on the increase in grain size relative to material above and below it. An OSL sample here produced an age of 190 to 910 CE, but again, I'm not sure that OSL is accurate or if it's an overestimate. Something important to think about, though, is where did all this sediment come from? Because this wasn't on the beach, this was onshore at several meters elevation. There's a few different explanations for this. You could say that it's from the last sea level high stand, but if this is an OSL age of, maximum 190 CE, then that's probably not the case. Another explanation is that you could potentially have it brought on shore by storms, but as I discussed in my thesis, the location of the Banda Islands is close enough to the equator that they really don't have a history of large storms here. You could have tectonic uplift take this stuff and bring it up to a higher elevation, but again, you run into the issue where this is, 70 centimeters deep, and it's potentially 2,000 years old. So that much elevation, or that much increase in elevation over that period of time seems like pretty much like a unreasonably high rate of uplift. The last explanation, which again I don't know, but I don't have a better explanation for it, is that these could potentially be tsunami deposits all the way down, and just that the only time Banda Besar gets a significant amount of sediment deposited there is when tsunamis happen. Because they have tsunamis, maybe every 100 years or so, but aside from that, there's no rivers or anything that might bring in large amounts of sediment. BA6 was kind of unique in that it was the only trench that didn't have any evidence of tsunami deposition. A bone from about 85 centimeters deep produced an age of 1400 to 1450 CE. And this is interesting because this would indicate a much lower deposition rate in BA6 than in some of the other trenches, even those that are really close by. And this could be due to a couple things. One, it could just be that there's naturally a lower deposition rate here, or potentially you could have material that's been removed by past tsunamis from this area. Finally, Trench AM1 has two candidate tsunami deposits. This first one up here contains some shell fragments as well as porcelain, glass, and stoneware and brick, but a children's glass cat's eye toy marble is associated with a maximum age here of 1949. So if this is a tsunami deposit, it would have to be the 1951 because that's the most recent tsunami deposit to hit this area. I've also got a candidate tsunami deposit down here, and this is a candidate not necessarily because it has marine material, but because it has a large assemblage of artifacts and is very coarse-grained. So if this is a tsunami deposit, which I'm not sure about, this would most likely be associated with the 1852 event. The overall purpose of this study was to determine whether tsunamis that have reached the Banda Islands and Ambon have left sedimentological evidence of their occurrence, and whether these deposits can be identified and dated. The findings show that recognizing tsunami deposits in these islands can be difficult, even in places that have had inundation. Future work would really benefit from digging a larger number of trenches within a close area, especially on Banda Neira, where I dug a bunch of trenches close by, and they produced pretty different trench logs. This could help in correlating sediment units across trenches, and could also help show you how much lateral variation there is in these candidate tsunami deposits. On Ambon, conducting additional trenching on the north side of the island, which was impacted by an enormous landslide tsunami in 1675, could reveal deposits with strong evidence of tsunami generation. I think if you're going to look for a no-brainer, obvious tsunami deposit, it's good to look where you expect to see the largest tsunamis, and that's definitely an area that's had a large tsunami. Finally, Chapter 5 is on reconstructing the source parameters of the 1852 Banda Arc earthquake and tsunami. In November of 1852, a pretty severe earthquake and tsunami struck East Indonesia. The earthquake's MMI was as high as 11, and the tsunami was particularly devastating in the Banda Islands, although it was recorded all over the northern Banda Sea. Because this was pretty instrumental, though, we don't know the epicenter, the magnitude, or any of the other parameters about this earthquake. Knowing these details, however, is important both for understanding the tectonics of the region and for future disaster mitigation. There's been some argument in the past that this part of the Banda Arc is incapable of producing megathrust events. So it's really important to know whether this event was a megathrust event, or whether it's not feasible that such an event could have come from this part of the Banda Arc. The main purpose of this study was to take quantifiable observations about this event, which were recorded in locations around the Banda Sea, and use them in a Bayesian statistical framework to try and decipher the most likely source parameters of the 1852 earthquake. This whole study is a joint effort by the WAVES team, which is an interdisciplinary group of researchers from several universities, including BYU. My own contributions to the project, and then kind of our broad strokes results are kind of what I'm going to focus on in this section here. But these involve finding and translating historical documents about the event, converting those observations into probability distributions, and then compiling bathymetry data for the tsunami simulation. In order to make priors to feed into the model, we needed quantifiable records of when, where, and how severely the tsunami struck at a variety of different sites. I tracked down and translated as many written records of the event as possible, and from those I isolated quantifiable observations. Some of these were really straightforward, like in Ambon Bay where they wrote exactly how much water rose during a tsunami. Others were harder. For example, this observation here talks about how people sought shelter on top of the pier, but they all drowned. So that gives you kind of a rough idea of the wave height, or at least a minimum, but it's not quite so well constrained as this observation up top. These observations and their uncertainties are then converted into probability distributions. Basically, this is communicating what are the odds that a particular observation is associated with a particular value, whether that's arrival time or shoreline wave height or inundation length on shore. The peak of each of these distributions, along with its width and skewness, depends on the nature of the observation. We made sure to make these distributions as accurate as possible to the historical records, while also still giving them an appropriate amount of wiggle room to account for any uncertainties that we have. Now, I don't have time to go into a ton of detail on how the statistical framework works, but the gist of it is that it takes all of the priors that we give it, and then it simulates hundreds of thousands of individual earthquake and tsunami events. And through this, the model is able to isolate what earthquake parameters are most likely to make a tsunami that lines up with those historical accounts. One of the most critical parts of making an accurate tsunami model, like I mentioned before, is having your accurate nearshore bathymetry. This was an issue for us because the most accurate bathymetry raster that we had was this one in the top right, which is really too coarse to be at all useful. To fix this, I basically followed the same methodology that I used for my Banda-Api sector collapse bathymetry, which allowed me to turn this into this here. We then combined that with the topography to get a full topobathymetric raster. Finally, along with the priors for the observations, we also gave the model priors for what we expected was geologically reasonable for the earthquake itself. We determined that even though we don't know where the location of the epicenter was, it would probably need to be somewhere along the Banda arc, although we don't know where on the Banda arc. So we told it, yeah, it should be on this arc somewhere. It's most likely to be maybe at this depth here, but it could be anywhere along here. And then after running the model, this produces a posterior, or kind of an end result, of what the most likely results of this event should be. So it turns this into this here. So each pixel represents a bunch of earthquake simulations, as far as latitude and longitude goes, and the brightness refers to the probability of that simulation making the tsunami that we saw. From this, we can see that the event most likely came from this part of the Banda arc, which is really cool. Here's another posterior example. The main heat map on this figure shows seismicity on the Banda arc during the instrumental record. So this is saying that since we've been taking records, like maybe since the 1960s or so, most of the earthquakes are down here in the lower Banda Sea. Our new model, however, suggests that the epicenter for the 1852 event wouldn't have been somewhere down there. It would have had to have been somewhere up in this region, where we've had very little seismicity. This suggests that there's a seismic gap here and that we could expect a recurrence of the 1852 event to happen eventually because there's active strain accumulating and not being released here. So overall, the final results in the model were really exciting. This is one last example. In our prior distribution for the earthquake parameters, we estimated that maybe the earthquake was probably likely to be less than a magnitude 7. We wanted to be conservative. The posterior, on the other hand, said that this was basically impossible and that the earthquake was somewhere above 8.5 and most likely somewhere in the 8.8 region, which again is, new to us because there's been arguments that this, isn't capable of producing an earthquake this big. But this shows that it couldn't have been a small earthquake. It would have had to be a large one. I just want to end this by saying that there's three main aspects of disaster mitigation that need to be addressed in order to save lives. The first is risk assessment, the second is risk communication, and the third is risk reduction. With this thesis of mine, I hope that I've been able to contribute to the risk assessment and communication regarding these particular hazards, and I hope that my results can be used to help in local risk reduction in the future. And that's the end of my presentation. Thank you so much for listening.